after the section. Just two announcements. We have a dinner tomorrow at 8 p.m. in this place, Estância Grill Churrascaria. Okay, it's a great opportunity to know the Brazilian barbecue. Okay? And we have one more talk today by Misha Verbitsky. This will be the last speaker of tomorrow. Tomorrow, yes. I'd say today. Yeah, we can do this today if you want, but I guess it's better tomorrow. Sorry, this is the right is in the book. Tomorrow, 6:20 p.m. Okay, one more talk. And now it's a great pleasure for me to introduce the first speaker of this section, Professor Marco Jardim from Gieseker. Professor Marco is a very strict geometry, algebraic geometry, and now he's the director of the very new Brazilian Center of Geometry. Marcos, please.
Thanks, Lino. Thanks for the invitation and everybody for showing up. So first let me talk some algebraic geometry, and then I'll do a short presentation of the Brazilian Center for Geometry that Lino mentioned. So this has a lot of slides, but my goal is to explain this picture here. So we'll start with the picture, and I'll repeat this picture several times. What this picture is supposed to represent is the following. So each point in this quadrant here is a Bridgeland stability condition. If you don't know what that is, doesn't matter too much. I'll explain very briefly what that entails. But in these lines, the black and the blue line, you can ignore the red line, are chambers, are stability chambers. Which means that for every point in this part of the plane, the set of stable objects does not change, and it coincides with the Gieseker semi-stable sheaves. I'll also come back to say a little bit of what that is. And in this other part, between the black and the blue curves, again, this is another stability chamber in which the Bridgeland stable objects are what's called a PT stable object. I'll also explain a little bit of what it is. And the whole point of this presentation is precisely to show this wall crossing here. So this blue line is a wall in Bridgeland stability in which objects, and I'll tell you how the Gieseker semi-stable sheaves get transformed into PT stable objects. So this is the whole talk in 5 minutes. Now let me spell it out a little bit. So first, what is a stability condition? Again, this is a very technical topic. Let me just try to briefly go over it. Initially talking about abelian categories. So stability, you start with an abelian category, which is this calligraphic A here, and then we choose a group homomorphism from the grothendieck group of the abelian category to the complex numbers, satisfying certain conditions. So the whole point is that the image of this map, or at least the image for the objects in the category, they all fall in the upper half, in the upper part of the imaginary plane. And with this we introduce a slope, which is minus the real divided by the imaginary part. There's this weird minus sign here, but never mind that too much. And that leads us to a notion of semi-stability for objects in this abelian category, which means that so an object is called stable or semi-stable if every sub-object in the abelian category satisfies this inequality here, either strict or not strict, depending on whether you want stable or semi-stable. So we also assume that any object admits what's called a Haber-Narasimhan filtration. So any object has a filtration by sub-objects such that all the quotients are semi-stable with respect to this slope. Okay? What that means is that any object in the abelian category can be built up from the semi-stable objects by successive extensions inside the abelian category. So what a notion of stability does is to tell you what are, to give a list of objects, the so-called semi-stable or stable objects, out of which you can build all the other objects in the abelian category by doing extensions. Right? So it selects a way to build the whole category out of a subset of these objects. Now, the extension of this notion from abelian to triangulated categories was done by Bridgeland, maybe already some 20 years ago. And it consists of 2 bits. Again, I'm going to throw some words around here, but they are not that important. The first part is the heart, what is called the heart of a T-structure, which is just a choice of an abelian category inside the triangulated category. And then a stability function in this abelian category. So never mind this word too much, it's just choosing an abelian category inside the triangulated category. And then maybe let me skip this. So now a Bridgeland stability condition will be now a choice of a stability function inside this this heart here, this other abelian category. And there is also involved in this whole structure. There's also this choice of a lattice and an epimorphism between abelian groups, finite dimensional lattice. This is also a way to select a bunch of objects out of which the whole triangulated category can be built up. So the most basic baby example is this example on curves. So if you take this abelian category to be the coherent sheaves on a curve, coherent sheaves, imagine that as vector bundles on a curve. A coherent sheaf is just going to be a vector bundle, potentially with some torsion sheaves or some skyscraper sheaves, things that are supported on a single point. And this central charge here, or stability function, will be the real part is the degree, or minus the degree, and the imaginary part is just the rank of the sheaf, and this is just like the rank of a vector bundle on the curve. There is an obvious choice for the lattice, and the whole point is that this notion of Bridgeland stability on curves coincides with the usual stability that was introduced by Mumford in the 60s. And there's been a lot of literature, a lot of history about that in the past, 60 years already. And the one important fact is that for a smooth curve, as I'm assuming there, every stability condition on the derived category of coherent sheaves on the curve is equivariant or is equivalent to this standard example. So all the other examples you can transform into this one. Two of the most important results in this theory is the so-called Bridgeland deformation theorem that says that, well, remember that you can make a set of all stability conditions on a triangulated category. This set, so every stability condition is a pair, right? So it's a choice of an abelian category together with a stability function. So this map here, just you forget the abelian category, you forget the heart of the T structure, and just send to the central charge. What Bridgeland shows is that you can choose a topology here so that this map is a local homeomorphism. And then in particular he can show that this stab is a complex manifold whose dimension is the rank of the lattice. The rank of the lattice because that this home from the lattice to C is just a big Cn, right? Where n is the rank of the lattice. So this was one of the foundational results that Bridgeland proved, that these things are complex manifolds. And then there is in this set, the stab, there is a wall and chamber structure. So in every compact set, every compact set will have only finitely many walls, finitely many codimension 1, real codimension 1 subvarieties with the following property, so that when you take the complement of the union of these walls, what you get is a bunch of chambers, right? So these are codimension 1, so they will cut this compact set into a bunch of connected components. And in each of these connected components, so called a stability chamber, the set of semi-stable objects does not change. Right? So my students know that I like the ant analogy. Right? So think of yourself as an ant walking in this complex manifold, and you are carrying in your backpack a collection of objects in this triangulated category, so a collection of objects, and you have a stability detector on your hand. And as the ant, and what the stability detector does is, it goes red every time one of the objects in your backpack, or in the ant's backpack, becomes unstable. Right? So when she's walking in this stability manifold, and the thing is red, and all of a sudden she steps into the imaginary line, one of these walls, and the stability, and this stability detector becomes yellow. That means that one of the objects in her backpack became strictly semi-stable. Right? So it's not stable anymore, but just semi-stable. And if she does a little ant step in the same direction as she was going, the thing becomes, her stability detector becomes red, meaning that one of the objects was stable, became semi-stable at the wall, and then it became unstable after the wall. Right? So the set of stable objects changes as the ant is walking in this stability manifold. Right? So what the ant does is, she takes the backpack off, selects the objects that became unstable, throws them away, replaces with some other objects that are now stable, and keeps on going with her stability detector until she hits the next wall. Okay? So this was another of Bridgeland's main result in his first paper about this topic. So some of the problems that have been studied in the literature, first is the existence. Right? So given an arbitrarily triangulated category, or given a projective variety, can you find stability conditions on the derived category of the derived category of coherent sheaves on X? Or can you find stability conditions on any triangulated category? This is far from obvious, and constructing stability conditions is not a simple task. There is a positive answer for surfaces, and for funnel threefolds, and more recently for PN and n-dimensional quadrics. The list keeps going. I'm not being able to keep track with the literature anymore, but a couple of months ago there was a paper posted on the archive claiming that any projective variety of any smooth projective variety of any dimension, you can always find a Bridgeland stability condition. And then it's the question about moduli spaces, right? So does this set of stable objects, does it have any geometric structure that can be that we can work with? In particular, the dream scenario, so to speak, and that's not saying a lot, is asking whether the set of all objects, of all sigma stable objects, so that's to say, objects that are stable with respect to a given stability condition, whether this is a projective scheme. And the answer is yes, again, for certain surfaces that has been proved. And more generally, one can only show that these are proper algebraic stacks of finite type. So in particular, it means that they admit good moduli spaces, which would be the candidates for these projective schemes. Right? So far, only proper algebraic stacks. I'm going to say a few more words about that as well. And last, what stable objects look like. Can you construct stable objects? Can you, given a point in that plane or in that quadrant of stability condition, can you give me an example of a stable object? Can you give me many examples of stable objects? Um, so coming back to the picture, as I said, each point here represents a stability condition, and imagine the ant walking here. She's going to carry Gieseker semi-stable sheaves in her backpack, and when she walks into this blue line, her stability detector will go off, right? And she'll have to change, take out her backpack and change all the objects inside to this other family of objects that I'm going to soon define. Maybe let me skip this part, because perhaps it's too technical. Let me say here what is a PT stable object. This is a less familiar concept. Maybe before, let me introduce, I want to explain what are the things in both sides of this wall, right? So firstly, let me say a few words about Gieseker semi-stable sheaves. So a torsion-free sheaf is going to is said to be Gieseker stable if every sub-object, every sub-sheaf will satisfy this inequality, where this P here denotes the Hilbert polynomial, right? So the stability here is not a comparison between numbers, but it's a comparison between polynomials. And this order in the set of polynomials is lexicographic order in the set of coefficients of the polynomial, from the highest power to the smallest power. So the highest power counts more than the lower powers. There is this similar or closely related notion here of a two Gieseker semi-stable sheaf, which is the same kind of comparison between polynomials, but now instead of comparing the Hilbert polynomials, you compare the Hilbert polynomial minus the Euler characteristic of the sheaf, divided by the rate. And then, two Gieseker stability implies Gieseker stability, which implies the semi-stability in the reverse order. And all these four concepts of semi-stability coincide when the Chern characters here are co-prime. Right? Again, technical condition. In today's slide, everything is going to hold. This condition is going to hold, and Gieseker stability and two Gieseker stability are the same thing in most of what I'm going to say here. So now about the PT stable objects. So we know, or at least I said briefly, what is on one side of that blue wall. Now let me say what is on the other side of the blue wall. So these are triples consisting of two sheaves and a morphism. This B is a two Gieseker semi-stable sheaf with satisfying this homological dimension at least one, or should be at most. This is smaller or equal, then not larger or equal. Sorry, so this is smaller or equal. So homological dimension at most one. Never mind too much what that is. Again, so it's some type of sheaf, and a sheaf is some singular version of a vector bundle. If you're more comfortable with this notion of a vector bundle. P is a zero-dimensional sheaf, meaning some vector bundle that is zero almost everywhere, except at some points. So the fibers are concentrated at some specific points.
PT is abbreviation or something?
Of Pandaripan de Thomas. Okay. And DT is Donaldson Thomas, from the title. And the third element in this triple here is some morphism, which you can understand as a morphism in the derived category, from the zero-dimensional to the shifted torsion-free sheaf, or an X2 class, right? Which satisfy again some open conditions, complete non-triviality. That I'm not going to say too much about that. And the theorem is that there was a definition before in the literature of PT stable objects that I skipped, and it turns out that the PT stable objects can be described by these triples here. These are the cone of the map alpha in the derived category shifted by And these objects really generalize what was again in the literature for the rank 1 Pandari-Pandit-Thomas stable pairs. So this is a notion that Pandari-Pandit-Thomas introduced in 2009, I think, but only in the context of rank 1. Right? So in other words, this sheaf B here is a rank 1 sheaf. It's an ideal sheaf of a curve. And this notion generalizes this Pandari-Pandit-Thomas stable pairs. Okay, so the wall crossing maps, these are, so this G here is the set of semi-stable objects on one side of the wall, the Gieseker chamber. This curly T here is the set of stable objects on the other side of the wall, the PT stable objects. And these are the objects that are stable at the, or strictly semi-stable at the wall. Or not strictly, just semi-stable at the wall. And these objects can be described as these pairs that I'm going to explain what that is. So in this sign, so this map here, this gamma map here, is takes a sheaf and sends to this object in the derived category where ZE is the maximal zero-dimensional subsheaf of the double joule divided by E, so it's some zero-dimensional sheaf. And E prime is some other sheaf that you construct in this way that has these two properties. It's two Gieseker semi-stable and has homological dimension at most 1. Yeah, so here is the homological dimension at most 1. So it takes the sheaf and it decomposes into, decomposes into these two bits, the E prime and the ZE, and rearranges in these two bits in some other way inside the derived category. And this map here just takes the two non-trivial cohomologies, right, of the PT stable object. The two non-trivial cohomologies are just these B and P here. So this is the H-1 and this is the H0 of the PT stable pair. So that's what the this map does. And there's this is on threefolds. There's an analogous version of these wall crossing maps in for surfaces as well. And for those of you that know about this, in the case of surfaces, the analogous bit for surfaces, this is the Gieseker Schulenbeck map. So this is a version of the Gieseker Schulenbeck map in 3 dimensions. Yeah. So two recent results about these two authors, Pavel and Tarjaka. They recently proved that the PT moduli stack is actually a projective scheme. So the PT moduli stack is actually, and the Bridgeland moduli stack at the wall, so both this thing and this thing here are projective schemes. And these are maps of projective schemes. And one important point here is, this is in stark, big difference with the case of surfaces, is that for surfaces, these wall crossings in Bridgeland stability, they tend to be birational transformations. Right? So in Bridgeland stability, these maps are not birational transformations in any way, shape, or form. So this map gamma here is a dominant map. So dominant means that the image is a Zariski open subset. And this tau here, in general, is not dominant. So in particular, these two things can have different dimensions, and will have different dimensions in several examples. So that's what I was saying. It's not a birational transformation. It completely changes the moduli space. A little bit of a history of the problem. So Pandari-Pandit-Thomas, as I mentioned, suggested, so they introduced the PT stable pairs, which is the rank 1 version of what I defined a few slides ago. And they said that their goal was to do some enumerative geometry. So I'm not doing any enumerative geometry. So they wanted to count curves and compare two ways of counting curves on a threefold. But they suggested that this DT-PT correspondence, which is the two ways of, because the DT and the PT are two ways of counting curves, or two ways of counting the same things. So they conjecture, or they suggested, there could be a correspondence between these objects, the DT stable and the PT stable, the Gieseker semi-stable and the PT stable objects. That perhaps this correspondence could be a manifestation of wall crossing phenomena in Bridgeland stability. So that's what we proved in our paper. That indeed it is. That there is a single wall crossing that takes the DT to the PT modulus. So Bayer established the rank 1 case as a wall crossing in a polynomial stability conditions with a slightly different version of polynomial stability conditions. And all these guys, Panaripan and Thomas, Bayer and Toda, Bridgeland, they're all interested in these DT-PT invariants, how these two ways of counting curves count the same thing, right? So how to translate one how's it called again? A generating function, right? So there's a generating function can be written in these in two different ways on the PT and the DT sides. They should correspond. They should, after all, they are counting the same thing. So how do you translate the coefficients in one generating series to the other? That's what they were interested in. And that's not what I do, what we do. We just look at the moduli spaces. And then Stock and Thomas proved the rank 1 case of these DT-PT correspondence, but then as a GIT wall crossing, right, which is slightly different from the Bridgeland stability wall crossing. And there was various proposals for a higher rank version of the PT stable pairs for a bunch of authors, and I think we now, since everything is fitting as expected in the context of Bridgeland stability, I think now we have the right definition for the PT stable objects. Let me give you a few case studies. First, this wall can be what's called a collapsing wall. Collapsing wall is that the wall kills every object. So every object that was stable becomes unstable on the other side of the wall, and and on the other side of the wall, the moduli space is empty. So this is what is called a collapsing wall. And that happens for this particular choice of the Chern characters. So rank R sheaves with C1, first Chern class 0, second Chern class 0, and third Chern class equals minus n. And this n here is always even. Depends on the way I write. So, so they can be anything positive. Sorry, anything positive. So on one side of the wall, the Gieseker moduli space has this description in terms of the punctual plot scheme, and the other side, the PT moduli space is empty. Right? So that's one version in which the wall crossing is the most radical, right? Because nothing goes to the other side of the wall. Nothing survives. Then there's this other extreme possibility, which is what I call a fake wall, right? In which the moduli of stable objects doesn't change. Everybody is stable. The wall, at the end, not even notices that it crossed the wall, right? Because the set of stable objects does not change. That's what I mean by a fake wall. And that happens for some particular choice of Chern characters, the Gieseker moduli space turns out to be the same as the PT moduli space. And then there is this particular case in which neither of these radical scenarios occur. So what happens is that on one side of the wall, the Gieseker moduli space is birational to a P1 fibration over P3 times P3. So this is the Gieseker moduli space. It has this surjective map to P3 times P3. The fibers, the genetic fiber of this map is P1. And then there is for a closed subset over the diagonal, right? Over the diagonal in this P3 times P3, the fibers are actually P2s, right? So that's why this is not a P1 fibration, but just birational to a P1 fibration over P3 times P3. So on one side of the wall, so P3 times P3 is the moduli space at the wall. Right? So this is the wall crossing map here. So this is the moduli space at the wall, just P3 times P3. And on the other side of the wall, the PT moduli space is again just P3, right? Which is isomorphic to the diagonal inside P3 times P3. So on one side, this moduli space has dimension 7, and on this side, the moduli space is only 3-dimensional. So that's the example of to illustrate that this wall crossing really changes completely the moduli space. One of the things that I'm interested now is how to generalize this picture, and how to, because this is working with a very particular set of Chern characters, right? So how do we expand this and be able to work on a larger family of Chern characters, and to understand, give a concrete models for the PT moduli space for wider varieties of Chern classes. Maybe I can give a rough idea of the proof based again on the picture. The argument was to well, it has a few steps. One was to characterize what are the semi-stable, the Bridgeland semi-stable objects at the wall. And then we also understood what are the asymptotically stable objects, right? So if you go to infinity in this direction, what are the stable objects? And then we found that these were the Gieseker semi-stable sheaves. And if you go to infinity in the vertical direction, what are the stable objects? And we found something that's not the PT stable objects. But if you go to infinity on a vertical line, and this vertical line is sufficiently negative, then what you get is the PT stable objects. And this was proved in two papers prior to the paper that I mentioned in the beginning of the talk. And then, so we knew the asymptotic, we knew what happened at infinity, and the task in this third paper was to fill in what understands what happens around the wall. So little below the wall, we found again the Gieseker semi-stable sheaves. A little bit above the wall, we found the PT stable objects, and showed that there are no walls between slightly above the wall and infinity. So there are no other walls in this region or in that region over there. So that was more or less the strategy that was accomplished in these series of 3 papers. 2 of them already published, and this is the one that's being posted on the archive. I was a bit fast on that. That was on purpose to give me a few moments, and so that you still have maybe 10 or 15 minutes of patience, so that I can do some advertisement for. I need to do this, and then. To say a few words about the Brazilian Center for Geometry, which is a CEPIG, FAPESP. This is the funding agency from the state of São Paulo, and they have a special line of financing, which is called the Research, Innovation and Dissemination Center. So that's what the Brazilian Center for Geometry is. It's a Research, Innovation and Dissemination Center. So these centers are funded by FAPESP, which is the São Paulo Research Foundation. It was established in 1998, so a little over 25 years ago. And we are supposed to do the three things, right? So research, but also innovation and dissemination of knowledge to society. There are nowadays 22 active of these RIDCs across various fields of knowledge. In ours, the Brazilian Center for Geometry is the first one in basic sciences. That doesn't have any applications or immediate applications. So this is a little bit about our mission, and in particular the strengthening international collaboration. Perhaps this is one of the goals of the present meeting. So some of the names involved. I'm acting as the director of this center. Henrique, that spoke earlier this morning, is the vice director, and Paulo Piccioli is the scientific director. Our colleague Marcelo Firer is the coordinator for innovation. I'll say a few words about what he does. Professor Rubia from UNESCO is doing the education and dissemination part. Carolina from IMPA, Carolina Araújo from IMPA, who is acting as activities and events coordinator. We have an international relations, which is Guilherme from the USCA, and Lino is the pedagogical coordinator of all this. We have four that we call the thematic verticals. One of them is applications of geometry, so it's general relativity, so space-time geometry. Applications to one of the areas that people do is protein geometry and also cryptography. There is the part about education, dissemination, and innovation. So it's curricular innovations, teacher education, and integrating technologies into math education. So one of the projects that is run by Marcelo Firer is developing ways to teach maths to deaf students, students that cannot hear. So how do you, there are no signs for the usual mathematical words that are used to teach mathematics at the basic education. Right? So how do you develop language for these persons with these disabilities to learn and explain maths? Then there is the bit about algebraic geometry, I'm also part of, that studies varieties, foliations, and birational geometry of varieties, modular spaces, which is my favorite topic, and algebraic geometric codes. And there's also the vertical into differential geometry. Right? So analysis of manifolds, geometric flows, geometric structures of manifolds. So a few of the names involved. So the part of applications of geometry is also led by our colleague Alberto Sá. Marcelo Firer and Rubia, as I mentioned, they do the part with academic research in school curriculums, but also educational outreach, right? So develop interactive learning platforms, and this is the project that I mentioned, Libras. Libras is the Brazilian Sign Language. To adapt mathematics to the Brazilian Sign Language for deaf students. Algebraic geometry is led by Eduardo Esteves from IMPA. Again, part of this story is also to connect algebraic geometry with commutative algebra and arithmetic. The differential geometry is led by Claudio Gorodsky from IME USP. Altogether, we are now 47 researchers. 12 of them are so-called principal investigators in the Southwest nomenclature. Basically, all the different universities and institutes at the state of São Paulo, plus a few others like INPA in Rio. This is a picture that's already a few months old of part of the team here at the University of Campinas. I'm wearing the same shirt. I'm almost wearing the same clothes. This is our international board with all the different areas of research. So Alicia, Hugo Bruzzo and Oscar Garcia Prada, they are in the algebraic geometry part. Bobby Akaria is in the applications of geometry. Bobby Akaria and Zilke Weinfuttner are in the applications of geometry. Differential geometry, we have Fernando Codá and Jorge Lauret. Short and Nitsa are in the education and innovation part. So this is our international board. So we hope to use the CPG, right, the Brazilian Center for Geometry, as a platform for new FAPESP projects like organizing conferences and bring visiting researchers to Campinas and other institutions in the state of São Paulo, and amplify our international cooperation. So we will see our application, our initial application to FAPESP had several, had the support from several international institutions, and we hope to interact more with them in the coming years. This perhaps is the biggest part of our funding. It's here in the 245 scholarships in all different types. So this is 20 postdoctoral grants. This is 20 PhD grants as well. This is for 5 years, for the initial period of 5 years. 20 postdoctoral grants, 30 master grants, and this is scientific journalism and scientific initiation. These are technical training grants for the part of the innovation and also really, and this is for teacher training. These EPs are for teacher training. So 245 scholarships. Altogether, our budget is around 32 million reais for the first. We managed to get one postdoctoral fellow that's acting as active manager, Juliana, and also two, and she's working with 2 undergraduate students doing supporting media and communication activities. So far, this is the wrong slide. Yeah. So far we have already implemented a bunch of these grants. I don't know why this is the previous version of this slide, but so we have already implemented a bunch of these 245 grants around. All of the EPs, a bunch of these TTs have already been implemented, and we are in the process of implementing the first 5 of these postdoctoral grants. Right, so we made an international call. There were 88 applications for 5 grants. We selected 5 candidates, and they will be starting their projects between this month, May, and next July, or next October, better said. All these 5 candidates will be starting their positions here in Campinas and in Rio Claro and São Paulo and so on. Hopefully, soon enough, we'll have some space in one of the buildings in the back, right? So the director is there, so maybe he will help us pay for part of this space in the building in the back. So this is the logo that Lino included in the very nice poster that he made. This is the logo for the Brazilian Center for Geometry. There's a website that I'm not going to show. Maybe people want to have a look at the executive project for this year that was done by Juliana and Patricia. And what else? And I'll end my presentation with this slide. So these are all the international institutions, universities, and so on that supported our original application to FAPESP. There are many of them, so that's why they are in very short, very small letters. Nobody can read them. This is just for shock value, and people to say, "Oh, yes, there are many." There are so many that we have to write in very small letters in the slide, and we hope to return their support in the coming 5 years, which is the initial concession for our center. Thanks, everyone, for your patience. Let me put my other farewell slide, which is this one. Thank you.
Any questions or comments? Marcus, this is stability condition here. You're working the threefolds?
Threefolds.
Okay, the Picard rank 1.
Picard rank 1. Still, we don't know how to generalize this to higher Picard rank.
And the Bridgeland map goes to the home of these lattices,
Yes.
which target in C or?
In C. In C.
Okay. It's a kind of, it's not covering map, right? Because it's a local homeomorphism?
Yeah, it's a local homeomorphism, but it's not a covering map, right? Because, because it's not, it may not be surjective.
Mhm.
So it's not clear whether any central charge, right? So first, not every map, this is a very good question actually. Not any map from the lattice, not every map here will satisfy the positivity and may not satisfy these, the conditions that are necessary for stability conditions. So this map may not be surjective. Right? And, for one thing, that's why this is not a covering map in general. But it provides local charts. Right? So what the deformation theorem says is that suppose you have a stability condition, then you can you can perturb it a little bit, right? You can modify the central charge a little bit, and it's still the same heart will you. Yeah.
Other questions?
Is there any positive characteristic version of this, or there's no?
Yeah. So in principle, at least the case of curves, you can do it, I think, without much. But then for surfaces, I don't know what changes. Positive characteristics.
Okay. If not more questions, let's thank Mark again. Let me give some announcements. There's a dinner tomorrow, 8 p.m. in Gieseker. Pascaria is a restaurant near here. We have the Bridgeland talk tomorrow, the last one, 20 p.m. And this is the third is here. Tomorrow, the conference will be in the back building. The building over there is called the Annex building. Okay, Marcus already told about this. In the room L004. And probably we will put some sign here, but just to let you know, it's in the behind building.
Can we enter the building, like it was already to be locked?
Yes, we will open.
Okay.
Okay, we manage this, I hope. Okay, I guess we'll move with blackboard. Let's just remove. And for me, it's a great pleasure to introduce the next speaker, the Professor Ludmil Katzarkov from ICNF Sofia, Bulgaria, and ISA, University of Miami in the United States. Ludmil is a great geometer, is a fantastic mentor, and my friend from
Thank you. So, very nice to be back here to Campinas. perspective, which will make it a little bit provocative. So it's some variational invariant. And so first I'll do it in a way historically. So the first approach is one of those input models. Then the second approach was with overall spectra. Then differential equations to the rescue. And then the final thing is the roadmap to further examples. So, of course, the main question by rational geometry is trying to solve is if x is variety over the complex numbers or some other field as well, as you're going to see, then if x is the same field of functions, that is the field of functions of n independent variables where n is equal to the dimension of x. So I'll spare you any historical remarks, and obviously this has been a problem that was considered by many algebraic geometers, first by Adam and Riemann, who found some obstacle in dimension 1, then by Italian school and Zariski, who handled dimension 2, then Griffiths and Clements dimension 3. But what can we do in that dimension? And one approach was first taken by mirror symmetry, and that is to start with x is projective and consider the category associated with it. That is the category of complexes of coherent sheaves. The x between them. So of course, in the interesting cases when this is a Fano manifold, this category as theorem for Loff and Bondo tells us completely recovers the manifold. So if there is some variational information that we want to study, it might be in this category. Now, according to logical mirror symmetry, we correspond to this category, another category of Lagrangians, and that is a category connected with open symplectic manifold. And then some potential And the statement of multiple Miller symmetry is that these two categories are equivalent. Now, let's look at one example. And that is the example of P2. So the derived category of P2 is a category which has an exceptional collection of the following objects. It has many others. And now, if you look at literature, the corresponding Foucault-Seidel category, started first by a physicist long time ago, and is the following. So you take Y to be, we start to the second, and this is the function that you want to associate with this symplectic manifold. Now, if you clear the denominators, you get that this is a vibration of open elliptic curves. That's the degree is 3, and we have 3 singular fibers. So you can compactify it, and so by Monchison we know that if you have elliptic vibration, it has divisible by 12 singular fibers, so we have at infinity some I9 configuration. And so that is the category that you associate with this data. So it's a category where the cycles are Lagrangian submanifolds. And the X are given by the floor homology. So we have 3 exceptional objects, and then the objects here are, they take a vanishing cycle, and you multiply on the path downstairs, and you have 3 singular fibers, and so this singular fibers should correspond to 3 Lagrangians. So this is what are called Lagrangian timbals, and this is how this correspondence is built. Now this is proven in a few cases, so that's why we will try to avoid it, but the observation that we make is that the geometry of this P2 is actually recorded by singularity 2A on the corresponding symplectic side. Now, let's look a little bit deeper at this Landau-Ginzburg model. So, how does it record the birational transformations? And if I blow up P2 in a point, what's happening here is that I have one exceptional object, and the transformation that is going to happen here is I kind of create one more singular fiber, and at infinity I'll have I8 singularity, and then so to these 4 exceptional objects I'll have 4 singular fibers. So the creation of this new singularity is what corresponds to the birational transformation. And so, in a way, you could think that at infinity you have some configuration which is responsible to birational transformations that you can even allowed to do. And then that is what we have on the finite part. And so the question is, can these things on the finite part be brought from infinity? And that's what we are going to be trying to find instructions when this cannot happen. Now, of course, this is a very simple example, and you can look at more complicated example, and we'll do this quite a bit today. And that is the main achievement of Pouch theory. The theory of intermediate Jacobian tells you that smooth three-dimensional cubic is not rational. And so the classical approach to this is by studying the following abelian variety, which has dimension 5 in this case, and you study the singularity of certain modular space called theta divisor, and because they are very small in this case, it cannot be obtained as a blowing up of P3 in some Riemann surface. That's the classical story, which uses quite extensively the theory of L Jacobians, then Andreotti-Meyer theory, and then Manford theory of free variety. Now, from the perspective of this approach to mirror symmetry, you have this symplectic manifold, and the function, the potential, looks like that. And again, if you analyze what this gives you, you are going to see that at the finite part, so you have a vibration of K3 surfaces, figure 4, one very singular fiber, which is intersection of 6 rational surfaces, and two other ordinary double points, singular K3s, and then some configuration, very complicated, consisting of rational surfaces at infinity. So, in any case, that corresponds to the fact that the derived category of this cubic looks like a fractional Calabi-Yau and two other exceptional corrections, and so the fractional Calabi-Yau is recorded by these singularities, and then we have two other exceptional objects. So now that observation led to the following theorem. Proven by me and Przylkowski. I think 2005, but it appeared 2007, which says that let X be a three-dimensional funnel with Picard of X equal to Z. And so let's say X is not P2, so it's not P3. And I mean, other Picards can be considered as well. I'm just doing this for simplicity. And then, so what you can do is, since this is a funnel, there will be always this fractional Calabi-Yau that appear here, and so you have the nearby fibers, and you consider the monodromy acting on their primitive cohomology. So because the Picard is Z, this is going to be three-dimensional, so around 3 lattice, and so the monodromy is going to be a 3 by 3 matrix, So in this case, the three-dimensional cubic is actually epsilon squared 1, where epsilon is the root of unity. And so the observation is that if mu is strictly unipotent, so x is rational, then mu is strictly unipotent. So in this case it's not. That's why the three-dimensional cubic is not rational. So this theorem is, the way it's proven is stupid. I mean, so you actually look at all these Landau-Ginzburg models and you look at this Cauchy list, you know which funnels are rational, and you just compare the monodromy with what you have from the other side. So one must say that Marcus knows this better. I mean, so I'm not sure how stable the classification of two-dimensional funnel is. So for a period of 30 years, it was improved by 4 more examples. So I was very surprised when in 2002 Mori actually added 2 more to this classification. And Kitchen did actually Nomura, but after some Kitchen observation did this 20 years earlier. So who knows? I mean, I think I remember Shifarevich mentioning once that classification of three-dimensional funnel reminds him a little bit of the classification of elementary particles. More money you put in the project, more particles you get. Well, this is as close as we are going to come to physics today. But in any case, so modulo that we have a classification, so that's a correct statement. And what we're going to try to do is to actually give a conceptual proof of this statement, understanding why this is the case. So now there's another sort of categorical approach to this, and that is related to the work done by Rouquet, and after that by Orlov, and that is related to so-called Orlov spectrum. So I'll briefly recall what that is. So let's say that we have a category, in particular derived category of smooth projective variety, of coherent sheaves of smooth projective variety. And then, so we'll consider T to be a generator. This category T generates via summons, triangles, and shifts. Let's say, did I leave anything out? Shifts. I think it's all there.
That's all.
Yeah. All right. So now, what we'll call generation time. So let's call it, sorry about this, G for generator and T for time of G to be the minimal number of triangles needed to get to any object in dBFX. So this is well defined and finite for dBFX. So we can associate this generation time for each of the objects in we generated in our category. And then Orlov spectrum for dBFX is just sequence of numbers, all of this generation time for the generators. So now, let me just give examples. So the category is dB of P1. This Orlov spectrum is it's 1 and 2. And so if the category is dB of an elliptic curve, the Orlov spectrum is 1, 2, 3, and 4. And so these are two curves, and as you can see, the first number is always 1, the dimension of the curve. And this actually corresponds to a conjecture by Rouquet that the first number, which is both also the dimension of the category, is always equal to the dimension of your manifold. Now this conjecture is proven in dimension 1, and the proof uses theory of capacity. Capacity theory is a breaking geometry developed by Viterbo, but it can be expressed in terms of the differential equation that we are going to introduce in a second. Now, approach to birational geometry was proposed by Orlov spectrum, and that is as follows. So, as you can see, we have in these sequences all these numbers that appear, and so basically there are no missing numbers in these examples, but the conjecture is that actually there are gaps in the spectrum, and the conjecture is, this is by Ballard, Zero. So is that so assume that the gap is bigger than dimension of x minus 2, then x is not rational. So it's a kind of combination of Rouquet statement and then this gap theorem. And if Rouquet conjecture is correct, that the dimension is equal to the dimension of your manifold, if you blow up something, so this will lead to a gap of dimension 2 or lower. And if it's bigger than dimension of minus 2, this cannot come from a blow up. That's why this is not rational. Now this spectra are notoriously hard to compute. So although it's a nice, well, maybe Alexei can tell you more, but it's an interesting statement. It is not very, very practical. So now, so I outlined two rationality approaches, and maybe one day someone will finish this approaches, but I don't have much time left, so I have to propose a shortcut here. And that shortcut will be the use of differential equations. Now, so we will use the idea of Landau-Weisbach model, and I strongly suggest you always keep it in your mind. But what is going to happen is, we'll study mainly funnels, and so this funnel will be considered as a algebraic variety, and so we'll use all methods that are available to us to study algebraic varieties. But we will also consider this X as a symplectic manifold. And so usually it's given by a bunch of equations in Pn, let's say hypersurface by just one equation. And then the symplectic form is the restriction of the Fubini-Spüle metric to your symplectic manifold. So we don't use these two sides of mirror symmetry, but we will just use one manifold, but with two different appearances, one algebraic and one symplectic. And so we'll come up with three different Hodge theories: classical, non-abelian, and non-commutative, which are going to produce one gadget, and this is so-called F-bundle, which I'll try to describe from this perspective. And so now so some things were already used, but once again, I mean, so there is more that one can actually use in terms of contributions from analysis, contributions from differential equations, contributions from moduli, and that is what I'll be proposing today. So, of course, the first thing is we have the rank homology of X with corresponding splittings from Hodge theory. And now what we would consider is the following thing. We take the algebraic cycles, well, let's say PP cycles. And so we will consider all these PP cycles, and we are going to build a Higgs bundle associated with this element of some Gieseker force theory associated with these 50 cycles, using them as a base. And so we'll consider the following Euler field, which is the quantum multiplication by the canonical class plus some deformation of it. So here we choose a basis of these PP classes. Ti is some variable, so some parameter. Delta I are these algebraic classes, and this is some constant that we are using here. And so now, when we are moving over this base, I mean, so we have different values of this Euler operator, or this multiplication. And so for each of them, for each choice of Ti, we have a covering here. We have eigenvalues of this quantum multiplication modified by these additional algebraic cycles, and that is giving us a finite one covering over this base of the PP cycles. And so this spectral covering is geometric realization of the this Euler field, or if you like, this Higgs bundle that we can associate with this situation. Now, to each of these points here, we actually correspond to a splitting of this known commutative, or if you like, to the corresponding homologies of your variety, but also taught as a symplectic manifold. And so we have a splitting of our Hopf structure over the this eigenvalues of the modified deformed quantum multiplication. And so for each choice of TIs, we have this splitting, and we have this splitting of the non-commutative Hopf structure. So we have a vibration of this different splitting for the non-commutative homology depending on the choice of this parameter. So besides the spectral covering, this finite covering, we have also a splitting of the homology, which vary over this base here. So now, the first and simple observation based on the work of Ritani is a theorem proven by Kuncevich, Pantefiu, which says that this splitting on these pieces is a birational invariant. This means that it modulo contributions of things that of co-dimension 2 and 5, this splitting remains constant under birational transformation. now, I mean, it is rather clear that if you have that this splitting is operational invariant, then you can ask yourself, well, which of these species correspond to algebraic varieties of codimension 2 and higher, and if you have a way of determining that that is not the case, then you would know that your variety is not algebraic. So let me do 2 examples. I'm sorry, it's not rational. So the example that we want to do is the intersection of cubic and quadric in P7. So we have this 5-dimensional funnel, and so it has a Koch diamond of the following form. Has others are 0. So we have this piece here, which is if you take 2 ones out, it is connected with the Koch diamond of the mirror of rigid Calabi-Yau. So now I mean, this is one of the 2 smooth Calabi-Yaus of dimension, funnel Calabi-Yaus. I mean, it's funnel, but it contains in itself the Koch diamond of Calabi-Yau. That's why they are called funnel Calabi-Yaus. And in a way, it's a higher dimensional generalization of what we know for 4-dimensional cubic, and all these Bushel manifolds that we have studied. Now, how do we proceed in this case? Well, we need to say something why you cannot get this Calabi-Yau in this piece, and the way to see that is as follows. So, so assume this theorem, and so you have a splitting of so some lambda 0, and then you have 3 others 1-dimensional atoms. Now, this piece here has only 3 algebraic cycles. So, it is something which has H0 of k, non-trivial. This one's emphasize this. So I mean, the argument from here should go like that. Assume that this piece comes from a 3-dimensional algebraic variety. So we know that there is no further splitting. This can be computed in many different ways, and you'll hear talks about this. assume that it comes from a three-dimensional algebraic variety, it could be singular. Now, this algebraic variety has a minimal model and a resolution which, because of these ones here, will be based on extremal contractions with fibers only curves. So in minimal model program you could have extremal contractions which contract surfaces, but in this particular case, as it follows in particular from a work of Corti and Koulogiros, so the minimal model will have a resolution which is done with extremal contractions which are only curves. And that allows you, using Grom-Witten theory, so you can show that the corresponding differential equation, the quantum differential equation, splits. So on two pieces, one which is connected with what you already have here as a singular manifold, and then some other things here. And so now, whatever happened, if I have three-dimensional algebraic variety, I'm going to have at least 4 algebraic cycles. So even if I resolve it due to the splitting, this will continue. And so there is no way, if I have algebraic variety here, if this piece corresponds to algebraic variety, to have only 3 algebraic cycles, as I have in this case. So this is telling you a possibility of arguing in this case that this quantum Calabi-Yau is not rational, with of course strong use of quantum differential equation plus minimal model program that we have invoked here. So already here we see that the quantum differential equation could be quite useful, and that's why we would like to look a little bit deeper of what does it have to offer. So, what is this quantum differential equation? So it's given in the following form. And this function of u is what is known from physics, gives you the corresponding values when you want to compute the rational curves into initially Calabi-Yaus, but then to other manifolds as well. And K and G, this is the operator of quantum multiplication when restricted to these PP cycles, and G is a certain grading operator. So in the example which I just erased of the three-dimensional cubic, K is, I always forget, is this correct?
Almost.
So what's wrong? And G, that's easier to remember, even I can. Is this matrix. So, in any case, so the solutions that you're going to get in this case are, so U in some power, let's say delta 1, and then you have some logs and exponents. And so these solutions produce the number of the rational curves of different degrees associated with this three-dimensional cubic. Once again, this matrix acts on the algebraic cycles of the three-dimensional cubic. Remind you that three-dimensional cubic has 4 algebraic cycles, so that's why this is a 4x4 matrix here. So now, I mean, using this quantum differential equation, you can actually see that you have splitting like that, and then an argument with the Serfanter tells you that this cannot actually, this 1551 part, which looks very much like the Hodge diamond of a genus 5 curve, cannot come from a genus 5 curve. But that's not what I want to explore here. So what we want to explore is the solutions themselves, so really get to the analysis. And what we want to look is at this asymptotics. So the value of this asymptotics is going to be demonstrated in a little while, but what we are going to try to do is, so we can't quite deal with the Landau-Ginzburg models, and we cannot deal with the Orlov spectrum. But using differential equation, we can record at least part of this information that comes from them, and replace, and maybe in some cases, that is sufficient for starting of questions of rationality. So now, so in this case, delta, there are two deltas. Actually, one is 5/3, and the other is -1/3, if I'm not mistaken. There are two possible asymptotics that you are going to get. And so the theorem I can formulate it in dimension 12 as well, but let X be a funnel. And dimension of X is bigger or equal to 3. So I can formulate a general statement, but let's do the simplest. So let's be a funnel hypersurface. So then delta is equal, this is the maximum, to dimension of X. Let's see. Yeah. So then dimension of X is, sorry, delta max is computed in the following way. Let's check the formula here. Correct? So, and then if delta max is bigger than dimension of X minus 2, X is not rational. So if this maximal asymptotic is bigger than the dimension of your override minus 2, then the conclusion is that X is not rational. It's a different way of proving that the dimensional cubic is not rational. So now you could actually use this quantum differential equation in a little bit more imaginative way. So remember that we had this splitting on different atoms. And instead of starting it all together, you can actually start restricting it on different combinations of this lambda I. Now that it's a little bit like trying to, if you think about it, trying to play with the Orlov spectrum and the corresponding semi-orthogonal decomposition. In fact, it's the same. If you have ever tried to use that to calculate Orlov spectrum. So we will really make use of this in our discussion. So we don't consider just one quantum differential equation for OX, but we consider this quantum differential equation with its restriction to different combination of these pieces that we get in the decomposition of the homology in this union of three Hodge theories, which I have described, which is called a bundle. So let me outline the roadmap. How much time do I have? Okay, so I have to cut it short. So let me describe this roadmap and do one example at the end. So you start with your funnel. And you consider this splitting on atoms. And then you consider the restriction of star to different combinations. So you could have that some of them are not included here. And you study asymptotics. So assume so that you have delta 1 to delta k as asymptotics, and K is equal to dimension of X, sorry, apologies, 2 times dimension of X minus 2. And the maximal one is bigger than dimension of X minus 2. Then you conclude that X is not rational. So this is sorry, case 1. Case 2, sorry, I should have done a better diagram. Delta I is equal to dimension of X minus 2. Then using minimal model program, for atom of course, so you conclude that, or don't, that depending on the result, then so in fact, that's what we did with this intersection of this Fano-Calabi-Yau. So the only combination actually that gives you this is going to be the atom in the centrum, and in the center, and then there you actually had that you have this equality, but with minimal model program you were able to conclude that this is not rational. Yes.
Are you talking about the very general one?
Yes, very general. So let me demonstrate. I mean, I can explain this roadmap, but let me just do one more example so that you see the point of it. So, and that is C3 in P7, sorry, P8. So now, this is, according to what we learned from Candelas in November, the most notorious Fano-Calabi-Yau. And the reason is that, so, I mean, 40 years ago when this was starting, Candelas actually started all this three-dimensional Calabi-Yau, and one of them turned out to be rigid. And so that's something that doesn't fit very well with mirror symmetry. And so in order to study it, he actually used the following observation, that if you look at the Horst diamond of three-dimensional, sort of seven-dimensional cubic, so it contains precisely this piece that we actually have for the intersection of quadric and cubic in P7, but of course we have more exceptional objects. So the corresponding splitting is this Calabi-Yau, which is rigid, and you have six more atoms which have dimension 1. So now the point that I wanted to make is that you can start combining these atoms and restrict your differential equation on different combinations that you get. But you will never be in this situation, in this example, unless you hit this piece. So all other asymptotics will give you something inconclusive, so this will not have enough asymptotics to claim that this is actually coming from algebraic variety. Now, that requires a little bit more work from the perspective of minimal model program, but I think that with some luck and so now my problem is that it is not completely clear until what generality this statements in minimal model program are completely proven. So certainly I think up to dimension 5 they are, and then you are in business, but that is to be discussed with the experts. But if minimal model program works until dimension 5, and you know that the corresponding Calabi-Yaos are resolved with extremal contractions which have big codimension, then this could be used, and combining the fact that it's only this piece which gives you the right asymptotics and this minimal model program, enhanced of course, you might be able to conclude that the 7-dimensional cubic is not rational as well. So for higher dimensions, I mean, we need a little bit more from minimal model program, which I don't think is done until now. All right, so I'll stop here.
Questions?
Yes.
So this is the atom of the Calabi-Yau 5-fold or 3-fold?
Threefold. So what we want to do is that there is nothing that looks like a variety that appears here. And that is because the corresponding asymptotics will fill these conditions. Yeah, eventually everything comes down to this 3-dimensional thing that you want to go out, just by the way we did it.
Yeah, that is, so the cubic is dimension 7.
Yes.
So if it contains
Yes. So the way so you want to assume that you have some 5-dimensional thing. Yeah, you combine these pieces with what you have here, but the asymptotics are wrong. Therefore, this cannot come from algebraic varieties. For algebraic varieties, the asymptotics they satisfy this property. And so you don't have so x is 7 here, and so you want this range of the asymptotics to be equal 10 to 10 here. There is no such a thing if you combine this. So this is how you do that. But there is one, and that is this piece. So you have precisely 6 asymptotics in this case, and the delta is equal to, the maximum is equal to 3 in this case. So you have to do this minimal model program in order to rule out.
Okay, but if the cubic was rational, and if that implied that some blob center was this Calabi-Yau 3-fold, then this blob center, this atom should appear 3 times because of codimension, right?
No, but I mean, unless you have done some radical extremal contractions which actually destroy some of these things. So, which is possible in this case since it's quite big codimension, it's codimension 4.
Questions?
So we do allow singular atoms and similar things. It's not only globes with smooth center. We know this use of minimal model was to do with that.
More comments or questions? If not, let's thank Ludmil again. Okay, we resume 4:30 with Leonardo, Cavenaghi, and then now we have some books.
Eu sim.
Já ouvi falar
Ele é forte. Menage métrica.
Let's start lecture today. It's a great pleasure to introduce Leonardo Cavenaghi from SNF Sofia. And today we talk about now 9.5 lecture. Showcase, I don't know what it is. But, and it's a very, for me, it's a very pleasure to introduce Leonardo because Leonardo is a son of this house. He did the undergraduate here and the master. And after the PhD, he moved to the USP later. But he come back here for postdoctoral and now he's working with Ludmil.
Okay. Thank you, Lino. It's always good to be the prodigal son. And I thank you for enduring and staying here until the very end. What I can try to promise is indeed a showcase in many instances. So what is the story of this, right? I've seen Ludmil's talk. It's a really deep subject, this is story. And essentially this atom theory was developed with the aim at solving problems in variational geometry. Although at first you would say this will never do this. As I'm sure Jardim will also explain, and many others. And the idea then was, let us try to more or less condensate the way that this theory was fought during 50 years. Because the original idea for the theory was based on many developments in mirror symmetry for many, many years. And the first time that Ludmil came with the reasoning behind this, it was 21 years ago. But the paper only came out last year, so there is a story behind it, right? Like a deep story and technical story. And then we have decided to put everything in something in 9.5 lectures. It's been like a very long journey since we are writing this. That's our current ongoing project. But that's not actually like lectures in the sense of only being instructive, but also to outline directions and questions and sketches of possible directions, partial proofs for many things, some complete proofs in other cases. This is the purpose of these 9.5 lectures. But what I wanted to explain here is actually how we are writing, what is the sort of reasoning behind it. And so I try to more or less divide this in two parts. Quoting Enrique, there's a lot of slides, but it's late. Let's see till where we get. Because it's definitely not homogeneous, but it is dense, the content. But let's try to make this nice and try to communicate what's going on. So what I aim to do, and let's see if I'm successful, is to explain Hodge atoms by the means of a coercion notion that fits already very well to many purposes in variational geometry, but more particularly in G equivalent variational geometry. So in this talk, whenever you see some X, I mean smooth projective variety of dimension at least 2. If you like, you can think of this as compact Kähler manifold. G, we always need a finite subgroup of automorphisms of this variety. And you're going to say that X is a G variety if this group acts genetically free from this variety. Then it's convenient to recall that you're considering actions to actually describe pairs. So we apply this notation to recall the pair. That's the variety with the group action. And you shall say that this variety with the group action is not G-linearizable if we cannot find a variational map between X and Pn where you see Pn with a linearizable group action. Think of this as you pick up a representation of a finite group and you take the projectivization of this representation. This is Pn with this linearizable action. So what we aim to do is to find obstructions to a smooth projective variety with a finite group action to be G-equivalent variation to Pn with a linearizable action. So the theorem that I chose to guide you is a version of a result was actually first established jointly with Lino, also using a slightly different method from what I'm going to approach here. But in this form it appears in this paper Atoms with Symbols, that's on archive with Ludmil and Maxime. That is for any multi-degree hypersurface sitting on P1 cross P1 cross P1 cross P1. So if you like, you can think of this as the blow-up of P1 cross P1 cross P1 on the curve. Then you can see it sit here on this P1 cross P1 cross P1 cross P1. And in this guy, you can actually consider the Z2 action that swaps first and second, and third and fourth factor. Now you assume that this hypersurface is invariant under the corresponding action, and the claim is that this pair here is no Z2 linear diagonal, meaning you cannot find a linear Z2 action on P3. This is three-dimensional, so it's hypersurface hitting this four-dimensional guy. You cannot find a Z2 equivalent variational map between X with this induced action and P3 with a Z2 action. And the same holds for X cross P1 if you extend the Z2 action to be trivial on the P1 factor. Okay? So I'm going to consider that this talk was a success if I try to convince you how to approach this question using this new developed theory of atoms. The first thing that I have to do is to explain what is theory of atoms. And I'll be slightly lying here in many instances. And one of them is that what I'm really introducing to you is a coarse version of atoms extended to G-equivalent setting that will serves well to our purpose. So skills number one, set up in a model manifold. So what is this about? What is the idea? So you pick your smooth projective variety, and then we know very well by Hodge theory, many informations are encoded on the homology of this variety. What we do is, you see its homology, its homology as a Q vector space. So that's why you put the name V here, right? Then you choose some homogeneous base. That has to do with this Euler expression Ludmil wrote. We're going to get there at some point. And then there you have point pairing. But something that you also want to do, I don't want to really to make many comments on that as you ask, is that you do not only treat this as vector space, but as super vector space. You make distinction between even and odd part of your homology. And to the choice of base, you can definitely keep track of the enhanced elements written in this base with the choice of these formal supercoordinates. Remember, the super here is just to remember you have an even and odd part. And you would like very much, because these things has an origin even in enumerative geometry, to keep track of curves. So you consider here, if you like, it's completely fine if you think there's some sort of a black box, this ring here of formal power series. We choose the symbols Q here, that we're going to treat by no-code variables. And then you can also do something a bit better, that is to consider this another ring here, this we call this null ring. Beta here are elements in second homology modulo torsion that actually correspond to classes of curves on your variety, so they're geometric. They come from actual curves sitting on your variety with your torsion. But you can consider as well this is likely extended, not is likely, actually really extended ring, this big enough ring, where in these variables that you took, remember that there was even and odd part. The odd part is actually stereo algebra, and then here you just pick your node covering, and you consider like power series whose coefficients are in this node covering and the variables are on the even coordinates. Why is that? Because this is the this will be the ring such that after you modify your Q vector space that we had before by tensorizing them, like doing the coefficient change to these rings, this Gromov-Witten invariance and has Gromov-Witten potential will allow us to define new products on our homology that in some semi-classical limit will recover the cup product. But we are like enriching in it with information coming from counting curves. So to be precise, we're going to call a potential any element of this big node call. And we can always decompose it as some classical part, meaning it involves only standard cup product, and some quantum part, which has like this sort of ugly expression. And these guys here, they track some numerative information. That's the fact. So you can define this potential. And we are going to use this potential to actually define families of new products on this Q vector space. That's the idea. But to make proper sense of this, we have like introduce these rings so that when you appropriately change the coefficients, you see, you can define new products. So what's the way to define new products? It's sufficient to determine how they are given in your chosen basis. And that's what I'm telling you here. So you have this potential, you take third derivatives, and these will be the structure constants on your new product. This depends on the choice of T. So it's actually a family. And this is the family of products that you are given. This family of products is always commutative. What can be guessed from the fact that you can permutate like these partial derivatives taking different orders. And it's a non-trivial fact that it's also associative. And the unit in cohomology is actually a unity for this product. So you have a priori this big quantum cohomology. We call it big quantum cohomology. Then the Q vector space after you extend the scalars to this node, and then define this new product. You call this big quantum cohomology. What is small quantum cohomology? It's just like you extend it to this guy and have this expression here. So you see there's like another enumerative geometry quantities. And these are this Gromov-Witten invariants, 3-pointed genus 0 of degree beta Gromov-Witten invariants. And one comes from another by setting some variables of this t equals to 0. So then you get rid of this t and just keep with this q beta that are these non variables. So let's see concretely in example. So what is the quantum cohomology of P2? Okay, P2 you can choose a distinguished basis where you have like the unity class in H0, then H is what we call like hyperplane class, and P is just H squared, H coupled itself, is the point class. Now we have these dual coordinates, T0, T1, T2, and the Gromov-Witten potential in this case is this. So you see, you have polynomials. This is coming from this classical part, and this is the quantum part. So Handel's power series on D, the degree. And what this guy here is, this ND, this is the number of rational curves of degree D passing through 3D minus 1 points in general position in the plane. This has to do with discounting in Gromov-Witten theory. Now, once you choose this base, is actually, we can explicitly describe the quantum product in this base. And this passes through considering these third derivatives, right? You see, and then it's specified by these quantities. This is an explicit example. Many things comes to mind now. Generically, this is power series. One could ask whether you could, two things already comes to mind. There's no geometry here a priori, but you have defined a product. How can you interpret this new product? That's a question you can make. Also, in general, if you give a smooth projective variety, how you can guarantee some sort of convergence for this potential? What happens is that actually, in this case of P2, if you treat this variable Q here as a complex number, chosen to have absolute value lesser than this number here, actually the potential converges. So the Gromov-Witten potential, in this case of P2, has a positive radius of convergence for this choice of Q. And this says in particular that you can find a germ of an open domain sitting, in the homology of P2, now with coefficients in C. And then the point is that at any point, so let's call this domain by M, so at any other point here, that's where I'm denoting this collection of variables T, we can canonically identify the tangent space of this germ with your C vector space, and just by considering the derivations corresponding to these variables, what the quantum product is saying is that you have a germ of open domain which has tangent space, and the quantum product is a product on your tangent space that is commutative, associative, and has unity. Okay? This is the point. Turns out that there is some redundancy here in these variables, in the sense that if you look, for instance, to this sort of expressions, you see that the corresponding coordinate that is related to age that lies on A2, it comes together with this Q variable here. This is something that happens in Gromov-Witten theory, and by the means of something that's named divisor axiom. Actually, you can pick on your H2 the guys, this is divisor classes, this class is an H2 lie on this Néron-Sebeck group, and take it out so that the precise picture after some cleaning, packing together these guys, is, okay, let us replace Q tilde with Q E T1, then you just assign it this new basis of derivations, and the quantum product, naturally, the same thing, not changing the expression. I mean, just, I said there are some lies. So let's say the quantum product is actually a product on this thing that calls logarithmic tangent value. So why logarithmic? Just simply because the derivation has this P2 layer. But this is completely general procedure. So whenever you have your smooth projective variety, you have its homology, and you can define the potential. And then all I'm saying is that you can actually get rid of some variables and obtain, whenever you have property of convergence, a germ of a manifold, such that the tangent space as a vector space is your homology, and the quantum product is nothing but a commutative, associative, unital product on the tangent, on this germ. But some problems naturally emerge. For instance, why are you considering the germ? And more importantly, it's an open question on whether, given a smooth projective variety, you can guarantee that the Gromov-Witten potential has a positive radius of convergence. So, what actually you can do about it, right? So let's just mark here what we have done so far, so that we do not forget. So your input is X, C, is smooth and projective. Then we have considered this A star XQ. We have considered the Gromov-Witten potential of X, its third derivatives, let's put it like that, yields unital, commutative, associative product in the tangent value of a germ But this passes through the assumption that the ground within potential actually will have a positive radius of convergence. And the problem is that we don't know this. So it's this open question yet. I mean, it's solved in many instances, but we don't know. So something that you do is, okay, let's not do this setup. Let us do something different. Let's work over some non-Archimedean field and try to secure convergence, not only in some formal sense, treating formal power series, but let us try to give a precise geometric meaning and hence being able to talk about points, not looking by some formal scheme or stuff like that. So you do this by introducing some auxiliary field. Maybe I'll not enter into details about that. But all that I want to say is that the idea for the next slide is to actually replace this M that you have defined by some variety, by some manifold that you're going to call a model manifold, where for the Gromov-Wittens defined there we actually have convergence. And let's be precise. Whenever you pick your complex smooth projective variety, you can define what is the A model manifold of this. And this is, just to keep in mind, the choice that you do so that you do not lead anymore with some germs that depend on convergence, but you actually build a geometric space with the following properties. So let's write it like that. Convergence is tricky. Then introduce some non-Archimedean field. Okay? And define this manifold Bx that's aimed to replace this M. Then in particular, for the points that you pick here, the desired property is that the tangent space shall be a copy of your homology, now with coefficients in this non-Archimedean field, and such that the Gromov-Witten potential will actually, by the means of this quantum multiplication, will give a product on this guy. So this is what we call a model manifold. Ludmil said about F bundles. An F bundle comes with an A model manifold and some choice of vector bundle over this times some this. Let's see if we get there. So maybe I'll skip this. So this is just what I said. You build this manifold that's aimed at to have these properties. And it turns out that it comes with a distinguished vector field, because now this is manifold. So we can do pictures. Maybe we do it here. Then you have your point. You have the tangent space. In these particular constructions, we ask the existence of some nice vector field that's called Euler at this point that Ludmil just wrote. And the quantum multiplication can actually be seen as some tensor field in Dx, which is actually a Higgs field. We generically don't use the practices of Higgs fields, and definitely not in this talk. The thing is that because you have tensor fields and vector fields on this manifold of yours, it makes sense to take the derivatives on the directions of these vector fields, and we ask that this tensor field is preserved by the derivative on the direction of this field. And it has this funny expression here. If you notice, for instance, that setting these variables TA equals to 0. You collapse the big quantum product to actually the small quantum product. And the Euler vector field reduces only to first Chern class. So this is element in homology, right? First Chern class. So it completely makes sense with this picture. And now that you have this, because your Euler vector field at this point, for instance, is an element here that has a product structure, it makes sense to consider this operator kappa b, that is, you have your Euler vector field at your point B, and you have like a product, have an algebra structure on that point. So this guy here is missing an entry, so you can pick an entry and just do this multiplication. So that's this guy is an endomorphism of your homology. And this is the starting point to do atom theory, this picture. Okay? I mean, on my perspective, and the perspective of these lectures, I know that Jardim and Ludmil, they are proposing different perspectives. That's the same, but this is geometric. So you have this story, and now we can actually talk about what is coarse Hodge atoms, once we have established the setup. So Ludmil talked about Gromov-Witten potentials. Sorry, about Landau-Ginzburg models. So what I want to propose is actually Gromov-Witten insight for these Landau-Ginzburg models. PQNL2 is smooth projective arrays, two Kähler manifolds. You can describe their Gromov-Witten potentials. The question is, what is the Gromov-Witten potential of their disjoint union? And you can define this as this external sum. In the same way that people who know hyperserver singularity theory, they have this Don Sebastiani type of theorem. You just add more variables that are independent, right? And the point is, the key geometric consequence out of this is that this A model manifold for this product actually is identified with the A model manifold of the disjoint union. Why this is important to us? Because if you want to do variational geometry, and so far we have not even touched this is purely geometric, differential geometry. It's important to understand how the things behave under blow-up, that are the elementary operations that you do in variational geometry. Because two varieties shall be variational, and there is this weak factorization theorem. They can be modified in one to another by sequences of blow-ups and blow-downs. Blow-downs are inverse operation to blow-ups. So if you really understand how these things behave under blow-up, you have a chance to try to extract the invariant separational geometry. And that's what we'll do. And the important choice for this is because the Vitani's theorem actually tells you a way to relate to this. First thing to say, something very tricky happens. Whenever you do blow-up of a smooth projective variety, there's a cohomological formula for this. Lopen, Griffiths, and Harris look, and that will be relating the cohomology of the blow-up, the original variety, and the center that you have performed your blow-up. But this is never really isomorphism. What is sort of hidden here, and Jardim will say more explicitly, is that under some careful choices you can actually promote quantum cohomology to the blow-up formula for quantum cohomology to a ring isomorphism. But for this setting that you are saying about A model manifolds, this becomes really geometric. So you pick X tilde to be the blow-up of X along some smooth subvariety of a dimension greater or equal than 2. Then you take your auxiliary variety here, that is Bx, so this the A model built to your original X, and you do the corresponding A model for the center that you blow up. So the center has coordination R greater or equal than 2, you just add R minus 1 copies of this. And the Vitani's theorem in this language says that you can actually find some open domains inside of this A model manifold in a way that it will preserve the quantum product and the Euler vector field. So tensor field you pull back, right? So it says that this map here is a pullback. So the pullback of your tensor field is the same on both sides, and push forward also represent. So this will mean that whenever you consider your quantum multiplication and you perform blow-ups, the corresponding contributions coming from the A model of the centers that you are going on, they will not interact with that of X. So you have a way to try to keep track of that. That's the point. But there is a left missing ingredient here. So now we just zoom in this picture. You have your dx. Hodge classes, Hodge homology, they are controlled by a certain group. In the sense that you can pick pure Hodge structures, meaning they are not necessarily associated to a smooth projective lines, but you can collect them and they will form a category. But this category is actually equivalent to a category of representations of a certain group that are not denoted by Hodge. This is Mumford-Tate group. And then this group here acts in your homology by giving the grades, by giving the grading of your Hodge structures, the decompositions of your homology. It turns out, because the way that we build the X, it will naturally act on your manifold, and hence we will leave a fixed locus. Of course, here I'm saying Q polarizable pure Hodge structures. But because I had to go to this non-Archimedean set to build this, we just consider the extension of this Hodge to this non-Archimedean field. And now it makes sense to consider points on your fixed locus, right? So for instance, you have this point. And remember that you have this operator and over here. So we have EUB and kappa B, EUB, B. These act on their fibers. Now let's make this B. Because this is an operator, it really makes sense to look to its eigenvalues, right? And hence to corresponding generalized eigenspace of it. So we can actually decompose the full tangent space for points here in terms of the corresponding generalized eigenspaces. So lambda belongs to the spectrum of this operator. But also, on the other hand, because you are in a fixed locus, it's very natural with your geometry to look to isotropy representation. So then, you also have this other decomposition here. Something that I must say to this group is pro-reductive. It means that you can decompose it in terms of irreducible representations. Let's put this as Vj. And what is the trick now? Why this choice of Euler vector field and this sort of stuff? Because Euler vector field and quantum multiplication, they are actually morphism of Hodge structures. So this means that these V lambda guys here, they are filtered by these representations. So the very a priori them looking right here stops being done at all. So these guys here, it's going to call coarse projectives. So shall be the splitting of your homology, because again, this is that are actually representations of your non-projective group. These are coarse projectives. But more than that, the tangent space, they have products, as we started explaining. So they're not only representations of what, but they are actually also unital algebras. So there are like many things that are important for many instances. So this is exactly what I'm saying. First, you can do this decomposition by isotropy representation, but also you have that one in terms of generalizing space. It turns out that they're compatible. And you call these guys projectives. But because you know blow-up formula, and you know that they don't interact, they behave like in a disjoint manner, when you do these respective blow-ups, all that you are doing is actually, let me just go, adding the contributions of x and of the center I-1 times. So you're just like adding your coarse Hodge atoms for the things that you blow up. Because you do that, you actually need a way to keep track of these guys. And one of these ways is, believe me, there are some invariants that are not really defined to these pieces, to these representations. One of them is this that we call rank of Hodge classes. This is what? So you look to your homology. Maybe I want to do it here, because now I don't need this picture anymore. You have your decompositions, right? Now you look to your homology with coefficients in Q. Then you have these guys, right? In QX. Then just look to alpha, lambda. I'm denoting there by alpha, but this is just the dimension of the corresponding generalizing space intersected with PP cycles, meaning with this summation. This is one environment. The other one is this Hodge graded Hodge polynomial. We're going to characterize it by the corresponding coefficient of the power k. That will be the dimension of the generalizing space when intersected with P minus Q X. That's what is written. So with these invariants and knowing all this theory that have been developed, you can actually try to look to this non-rationality criterion by Katzarkov, Fontsevich, Plantek, and you. Whenever you have X any dimensional smooth complex projective variety, if in this decomposition, meaning if it is in this generalizing eigenspace that are actually representations or even unital algebras that we call atomic composition, does not appear, if there is a coarse Hodge atom, meaning a representation, that does not appear in the atomic decomposition of a variety of a dimension up to n minus 2, it's not rational. That's the statement. So you have, how do you proceed in practice to solve problems in this? So you compute the action, compute the generalizing space, look to this decomposition, and then you have a way to keep track of them. And then you have to know actually what are the possible representations that appear in the decompositions of varieties up to dimension n minus 2. And once you know this, you can try to apply the criteria. many difficulties arise. Many, for instance, at this very point, the theory can be successfully applied in dimension 4. Because to understand this, you have to know all the possible atomic content of points, curves, and surfaces. Because these are the things that you can do blow-ups. But if you want to do something in dimension 5, you have to know what are possible atomic contents for threefolds. And that's something in progress. But as I said, our interest in this talk is to actually look to G-equivalent variational geometric problems, this linear divisibility result. So all that you have to do is simply extend this theory to the G-equivalent setting. So you have a smooth projective variety, you have finite group action, right? And then you have the fixed locus that I have described. But because the group action on the variety actually induces an action in cohomology, you can to define also an action on this, on your dx, and now you don't look anymore to the fixed point by Hodge only, but Hodge cross G. And now the representations that we're looking at in the algebras are for these Hodge K times G modules. Then you have to prove that an Editalis result will extend accordingly to this point. And once this is done, you can actually apply the theory likewise. When new invariant comes, that is just okay. So instead of only looking to Hodge classes, let us look also to invariant Hodge classes by the group action. And this is how we approach this sort of questions. I kept saying about algebras and this sort of stuff. I said like, why do I care about this fact being an algebra in many instances? It's because this means that we always have one Hodge class, because this is the unit of the algebra. It's preserved by the action. And in the equivalent set, we always have one equivalent Hodge class. Also because it's an algebra, so it has preserved the unity. So that's one point, because among the many slides that I'm telling you and not telling you, the others that I'm hiding, this point that we're performing our computations here, it has to be general, no? As Jardim most likely will add details on his perspective on that. And something that I didn't say, and I should, because this is crucial, is not at any point that you are doing this computation, but at any point where you have the maximum number of distinct eigenvalues. So in practice, you don't know where you are if you are in this point or not. What you do is actually restrict to this small quantum cohomology by setting all coordinates t equals to 0, and perform your computations with a small quantum cohomology. Then there are many methods. Giovanni, for instance, is going to talk about one of these methods. And then you have to actually know that you are in the point that gives you this maximal number of eigenvalues. Sometimes you don't need it. I mean, sometimes you get obstructions already. But one way to try to keep track whether there's further splitting or not is because of this property that you cannot lose invariant Hodge classes. So in this case, the motivating example that I gave you in the beginning, it was a threefold with a Z2 action. We want to understand whether this action is linearizable or not. And to do that, because then we have to know this atomic content, like for varieties of a dimension up to 3 minus 2, that's 1. We have to determine what are the atoms like for points, G equivalent atoms for points. Points are curves. And you can put them on a table. So the point is, every atom appearing in the composition of varieties up to dimension 1, they necessarily must have either 1 or 2 invariant Hodge classes. And if the polynomial, this Hodge graded polynomial is constant, necessarily it has to have only one invariant Hodge class. That's what we do. And so in this very example, when you compute the eigenvalues, you can actually get to some precise numbers to them. What is the example again? It's a rational variety over C, because it's the blow-up of a P1 cross P1 cross P1 along the elliptic curve. And now we're considering a Z2 action induced from the ambient, where you swap one first and second and third and fourth factor. And finite group actions and questions about linearizability, they have everything to do about questions in variational geometry over non-algebraically closed fields. So for instance, this question over Z2, you can really think of this as questions about rationality over real numbers. Because the finite group will play the role of like the Galois group of extension to of the algebraic function. So, but again, I mean, this is only some motivation. But you have three different eigenvalues at this point that we have to compute here, and it has its corresponding variance. So the generalized eigenspace, or the coarse Hodge atom corresponding to eigenvalue 16, it will have only one Hodge class and only one invariant Hodge class. This is all computed. I'm just saying to you the answer. And it has this Hochschild polynomial constant equals to 1. Now for the eigenvalue 4, you have 4 Hodge classes and 2 invariant Hodge classes. And you can show to have Hodge polynomial constant equals to 4. Now there is the eigenvalue at 0, and it has 5 Hodge classes and 3 invariant Hodge classes. But it has this tricky polynomial. So all that you have to do now is to show if there is an atom here that do not appear in the atomic decomposition of points or curves. And the way that you do this, you look to this complicated stuff. Then you remember the Hodge polynomial of this variety. So it's like 1, 4. This, I never put the zeros, sorry, it's contagious. So you know here that there are some classes that are transcendent. And they happen because they are blowing up Q1 plus Q1 plus Q1 in elliptic curve. So you know that the atom of the elliptic curve has to appear in this decomposition. And this, it appears here on the 0 because you have no constant Hodge polynomial. Now let us just disregard the corresponding contribution. You can check that the atom of the elliptic curve contributes with 2 Hodge classes and 2 invariant Hodge classes. So the remaining quantity appearing in this atom at 0, that's like 5, 3, so deduct this 3, 1, it has to appear like in the atomic decomposition of points and curves. But this means that the remaining invariant 3, 1 has to be a combination of the possibilities of Hodge classes and Hodge invariant classes that are not that from its curve. So it would mean that this 3, 1 has to be written in terms of non-negative contributions for these guys. But this is just not possible. So you conclude that there is an atom here that does not appear in the atomic decomposition of points and curves in this one. And that's how you prove the result. There's a lot of, you see, to define it, to check it, to do blow up, to even like define Hodge atoms is more difficult than proving. So after, of course, with some light, right? If the numbers to you are given, some like a word of warning. It's really difficult to compute these eigenvalues. I mean, it requires a lot, as I hope the one especially will convince you. It's hard. It's really hard. But once you do this, you can analyze. A comment that I would also like to make is, in this atoms made symbols paper, we can actually state some, let's put partial theorems, like pending theorems, so that we can apply atomic theory, Gieseker variant atomic theory in all dimensions, but it's missing something. that I'll not ruin the surprise. I'm gonna have to go there to check what is it. But it's missing something. Once this something is proven, you can actually extend this to larger settings. And pretty much this is what I wanted to say. I just would like to put one sentence on about what Ludmil said. Really one sentence. I mean, I want to go over time, I promise. So the arithmetic of dimensions, because if this numerology here is mysterious, it can even get more mysterious by just rephrasing this theorem that Ludmil just stated. If you have a smooth complex projective variety of dimension greater or equal to 2, there is these dimensions that he was computing, and if this is greater than I minus 2, then the variety is non-rational. And when you do this, for instance, for cubic threefolds, quintic fourfolds, quartic fourfolds, products of quintic fourfolds and products of quartic fourfolds, you get many results out of nothing. But what is this nothing is also some y. Because to determine this number, you have to solve a differential equation. That's this ugly. So I said that once you have your Bx manifold, if you consider some auxiliary variable u here that lies in analytic disk, a germ of analytic disk on the affine line on your non-Archimedean field, you can define what is a model F bundle, and it has a distinguished connection with has a pole here. This is this Euler, this is the operator. So you want to solve this quantum differential equation. And you solve this by the means of an ansatz. So the ansatz also has as next point your eigenvalue. And then when you look to this guy here, this leading term like this S here, so then you can actually define a dimension by looking at all the possible solutions. I'm going very quickly here, just saying some words on what Ludmil said. And then after this is done, after you solve all of this, indeed, you get for the cubic threefold 5/3. And 5/3 is definitely greater than 1, so this is why observation. But I mean, there's a bunch of like analysis building here to make these things really formal. It's really some hardcore analysis over non-Archimedean fields. But essentially, this is what I wanted to say. Thank you.
Questions or comments?
No. So in the usual case, not the invariant case, you take Bx as the homology, and you're taking classes that are invariant under the Hodge action.
Yeah.
But in the equivariant case, are you also taking the same Bx, or are you taking...
The Bx is the same.
The Bx is the same, it's not like the equivariant homology.
No, I mean,
I thought it would
no,
be.
but that's an important question, because
Yeah.
you could say, what is the model F bundle for equivalent homology? The point is that then appears mixed Hodge structure, so I have to deal with mixed non-rotated group, and most likely you want to look to different sort of problems. So it's the same Bx, all that changes is the fixed modulus. But so this is an important question indeed. You have to look to this fixed. The definition of Bx is the same. You don't go to equivalent homology. This is really important and subtle point. This is something else. I mean, it solves other problems, especially that there's many issues. Like there's different grading that you have to consider. Euler vector field does not preserve the grading, and it will be a mess, but it's solvable. And there will be a talk related to that in this week. I'm just not seeing the speaker. But yeah.
More comments?
Yeah.
Question. So, in all of this, X was a projective variety.
Yes.
But considering that the property of being projective is not a birational invariant, does all of this make sense when X is Moshe's on, for example?
So I can say to you something about the quasi-projective fields. We can define a notion of a Gromov-Witten. This will be in this lecture, right? So when X is quasi-projective, only I don't know about motion, but my point is, the first thing that you want to do this business in this manner is, what is Gromov-Witten theory in the context that you are looking? If it has one, then you pretty much go to start. For instance, you can do this for quasi-projective variety, you can do this for orb folds, and that's the secret that's in these atoms. It's in the symbols paper that I'm not telling. But like for more general, for instance, singular varieties, if you can make a way to define Gromov-Witten invariance, but it's essentially combinatorial. I mean, it has to do with the Giovanni's talk. You can just use this formalism that's in operads, and then you can do this. But this is the first initial obstruction that you have to accomplish. So that's why we are in this smooth projective setting. Also, for pairs, it's possible, but it's not done because I mean you have to do it with Gromov-Witten invariance, and I would say you have to prove a law form in this case for sure. And yeah.
More questions? Okay, let's see. And we have a small opening ceremony in 5 minutes to start.
Você tem uma sequência. Todos esses estáveis, tá? Todo mundo estável. Então aí tentando traduzir para ele. Você tem uma sequência de Schleifstein converge por uma coisa que só tem singularidade pontual. Então, o desafio é como é que a gente transforma esse exemplo que eu tenho numa análise de...
Okay, so good afternoon, everyone. If it's already by the end of the day, now it's the opening of this conference. I would like to welcome everyone to IMEC and to UNICAP. This is the first edition of Campinas Miami Mathematics Conference, mathematical meeting. We hope we have a second, third, and fourth, so on editions. I will play here both the role of the welcome everyone as the director of the institute and also serving as the master of ceremony for this very informal opening ceremony. So I'd like to greet my colleagues at the table, Professor Lino Grama, Professor Jacqueline Mesquita, Professor Ludmil Katzarkov, also Professor Rafael Diaz from the UNICAP Office of International Relations. Professor Ludmil is the coordinator of INSA at the Institute of Mathematical Science of Americas, and he has strong connections with WIMEC, mainly with Lino, Jacqueline, and also Leonardo, that is somewhere. And I would like here to recognize the enormous support that INSA gives to Latin American mathematicians, also for a lot of initiatives of Brazilian Mathematical Society. And INSA supported some of the events that we have organized here in the last year, in the couple of years. And it's a pleasure to us to host this event because mathematics is very important to strengthen collaborations. Our main research equipments beside our brains are precisely these connections that we build in the conference. So I wish everyone an excellent event. And well, now I return to my role as the Master of Ceremonies. I would like to invite Professor Lino Grama to say some words to you on the behalf of the organizer of the conference. Please, Lino.
Okay, thank you, Ricardo. I guess I speak enough microphone. And okay, very quickly, welcome everybody to Campinas, welcome to University of Campinas, to Mathematical Institutes. We are very happy to have this conference here. And I just would like to say thank you for our sponsors, because, okay, organizing a conference in Brazil or more general in Latin America is always an adventure, is always very excited, and we have a lot of to help us. And the first one, CAPES, is a funding of the agency funding, Federal Agency of Funding. The FAPESP is a state funding. The Brazilian Center of Geometry, as the director is Marco Jardim, help us out. Thank you. And IMEC, say thank you to Ricardo, a lot of support for this conference. The INSA, Professor Katzarkov is the director, helps a lot, our initiative here in the IMEC, through the America Latina also, and the NSF and Simons Foundation. And we have a very nice schedule for during this week, a lot of geometry, a lot of math, and I hope everyone enjoyed this conference. Thank you.
So now, please, Professor Jacqueline Mesquita, to give some words. Lino, please give the mic to the Jacqueline. Jacqueline is the organizer of the event, and also she is the president of the Brazilian Mathematical Society, and also the president of UMALCA, the Union of Mathematics of Latin American and Caribbean. Okay, Jacqueline.
Thank you very much. Good afternoon, almost good night to everyone. It's my great pleasure to be here today. First, I would like to thank you very much, Lino, for this organization. Lino made a lot of work in order to provide this conference, and I am very glad to say some words on behalf of the Brazilian Math Society and the Mathematical Union of Latin America and the Caribbean, since these type of initiatives are really important for developing mathematics in the Latin America and the Caribbean countries. And this collaboration with INSA is really important. INSA, through the years, helped a lot, many initiatives in Latin America and the Caribbean countries, always supporting conferences and consolidating a lot collaborations. Here in IMEC, Unicamp, INSA has several collaborations. Ludmil, together with Lino and others, brought these very strong collaborations in geometry. So it's really nice to have this conference now, like this joint meeting, Campinas, Miami, here at IMEC. So I'm very glad about this initiative. I hope that from this initiative we can have fruitful collaborations and start new collaborations, consolidate the ongoing collaborations. And I believe that it's really this relation between INSA and IMEC will give a lot of fruitful things for mathematics in the future. We can see a new generation of mathematicians working collaboration, going to Bulgaria, going to United States, going to all these environments in INSA that Ludmil is the director of INSA, and also construct all this relation between Bulgaria, Brazil, United States. So I think it's really important. So I'm very glad to see this conference. I wish you very inspiring days, that you can also do a lot of high-level mathematics during these days and start new collaboration. So thank you very much.
So thank you, Jacqueline. Now I invite Professor Ludmil Katzarkov to say some words to us on behalf of INSA and also on behalf of the organizer of this event. It's on.
All right. Hello everyone. I've been many times to Campinas, and I know pretty much each and every one of you. So there is no need of introduction. I've been coming to Campinas for many years now, and all these collaborations that were mentioned were established because of my visits. So I'm very impressed with the steady progress that especially young Brazilian mathematicians have made for the last 20 years. And so I can promise you that we'll just bring this collaboration to the next level. not only with the United States, but with other European countries. Of course, the Bulgarian-Brazilian connection in Campinas exists for many, many years now. I don't see Plamen and Desislava, but of course they have been here much before I have been, and we hope to really deepen the connection there even more. It's nice to see that there are some representatives of the Russian School of Mathematics here, and hopefully under better conditions we'll be able to deepen this connection as well. Looking forward for a great conference here and then in Rio. I'm sure that the future is bright, and this is only the beginning of even more meaningful collaboration, even in more area of modern mathematics. Thank you very much.
Oh, thank you a lot, Professor Ludmil. Now I invite Professor Rafael Diaz, Executive Director of International Relations of UNICAMP, to say some words, please.
Well, good afternoon, dear colleagues. The stable, Professor Lino, Professor Jacqueline, Professor Ludmil, and our host, Professor Ricardo, as the head of the Institute of Mathematics, Statistics, and Scientific Computation. It's a privilege to join this activity as representative of the Rector's Office, in whose name I welcome you all to UNICAMP, for those who are visiting us. Well, and it's also very significant that this kind of activity done by IMEC have become a staple at the university. So IMEC has a history since its beginning of being a very international school with professors from different parts of the world, from Europe, from the US, from Asia, and of course Latin America present. And we see this embedded in the DNA with the number of international activities done by this school. So it's very good to see this happening on a regular basis, fostering not only cooperation and friendship between different parts. And I see that Professor Ludmil, we met recently during one of your last visits, so I can pay witness to the fact that you are here on a very regular basis, and this is, of course, what we expect with these partnerships to connect these bridges that, as mentioned by Professor Jacqueline, are the ones that make cooperation possible in terms of teaching, research, and elevates the quality of what we do in different fields, and mathematics is no exception, of course. So welcome you all. I wish you a very productive workshop over this next days. Thank you very much.
So thank you a lot, Rafael. Okay, we will finish the opening ceremony of the event by here, but I have two important information to give. First of all, that tomorrow the conference will be in another building. It's the called Anexo 2, the second Anexo of the IMEC. It's you can, if you are here in the auditorium, you can go downstairs and leave the building by the library door, and then is the first building. But perhaps we will be around here to take the
building in the back.
It's the building in the back of this building. And also we have the conference dinner tomorrow at 8 p.m. at the Estancia Grill, and everybody is invited. So okay, so thank you all for the presence. I hope that you have a good conference of these next 2 days. Thank you.
Na verdade, a gente não existe